Before starting the session, I just wish to present a brief profile of this resource person, Dr. Lajish. So Dr. Lajish, besides being a faculty member of Department of Computer Science, he is the director of Calicut University Computer Center too. He holds PG degree as well as PhD in Computer Science. He has around 4 years of industry experience as scientist R&D in TCS Innovation Labs, Mumbai, and around 11 years of experience as faculty member in Department of Computer Science, University of Calicut. His interested areas are computational intelligence, data analytics, Indian language speech, script technology solutions for masses, digital image processing, and pattern recognition algorithms. He is a recipient of prestigious Tata Innovista Leading Edge Award in 2009, Dr. APJ Abdul Kalam Lifetime Achievement National Award in 2017. He has 1 US patent, 2 Indian patents, 2 books edited, 4 book chapters, and more than 75 research publications in reputed journals. He has successfully guided 4 doctoral and more than 10 MPhil research scholars in computer science. At present, he is holding the position of Chairman, PG Board of Computer Science in University of Calicut. So I hope with this session, you will be benefited a lot and you will be acquainted or may taken deep into the different aspects of machine learning and deep learning. So I invite the resource person, Dr. Lajish VL, to handle the session. Thank you.
Thank you, ma'am, for the nice introduction. So thank you for that. And let us begin the session. So hope you have enjoyed the first session, which was handled by Professor Isaki Raja in the morning. So he was giving nice introduction about the digital signal processing, followed by digital image processing in the second half. So in this session, as mentioned by Anjula ma'am, so we'll be more focusing on the introductory level of machine learning, starting with the perceptron to the deep neural network in a qualitative way. And some of the research activities that is taking place in the Department of Computer Science, so that budding researchers from this participants group can associate with our department in future for your machine learning related research activities. So you are most welcome to the Department of Computer Science for the collaborative research activities. So that is the main intention of this particular session. And let me share my screen. So I think you can disable the screen, right? My slides. Okay. So thank you very much for this opportunity. Let us move on to the succeeding slides. So the goal of this talk is to provide perspective for those who need to really understand the background and the scope of computational intelligence. So that is the baseline of the task of this talk will be based on the computational intelligence and activity. So could you please switch off or mute your mic so that other participants can listen to me, right? And basics of machine learning. So the webinar is titled Advanced Machine Learning and the Signal Processing. So most of the work that we have carried out in this line on. So signal processing and machine learning for signal processing. And machine learning, starting from the perceptron to deep neural network, will take a walkthrough on the ML story and innovations in machine learning. So as I said, this is to inspire you towards this machine learning related activities, especially emphasis on signal processing. This is a nice combination you can also think about working on in future. So I'm happy if you could stop me at any point of time if you want a discussion or any clarification what I say, or if you disagree with my points, whatever it may be. So let us make it more interactive so that our future collaboration and activities can be start from this session, right? The question is, the outline of the talk is essentially, they start with the question posed by the famous mathematician and computer scientist Alan Turing in 1950s. Can machine think? So this was the question asked by Alan Turing, and that comes the importance. There comes the importance of machine learning and perceptron and multi-layer perceptron. So how it differs and what are the activities that we can normally carry out. Uh, and and now, as you said, so if you go further in machine learning, the hot topic or the buzzword in the industry and academia is the deep neural networks and and after that CNN and GAN, etc. So you will be getting a detailed introduction about this deep neural networks related research in tomorrow's two sessions. So we'll get we'll set a stage for handling it or to understand that high advanced topics on deep neural networks, which is scheduled tomorrow. And definitely, this will be associated with very research challenges and problems associated with that. And essentially, we are looking to the young researchers, those who can really contribute on developing or conceptualizing or prototyping various innovations related to machine learning. So our is an applied branch of science where you can really go and implement such applications for the common man or the people around you to solve a real life applications like that. So what is your answer for this question? So those who have listened to me previously, I have posed this question to many of our research groups and students around me. Whenever I get a chance to discuss with the students, I pose this question to the students. So this is not asked by me. As I said, this is the question posed by Alan Turing in 1950s. You see, right? Just still, this question is very relevant. What is your opinion on this? Can machine think? So we'll start this. So this is the afternoon session. Definitely, you will be a little bit tired. You're after listening to the morning session and all. So let us make it more interactive. So anyone from your group or from among the participants, if you can unmute and say, what is your opinion on this? Right? Remarks on this. Can really machines think? So what is your answer for this question? So you listen this, you carefully watch this slides where I put this type of paintings. So I will tell you the story behind it, right? So anyone from the participants, any student participants here? It really matters that how you respond to these questions. That makes difference. So tomorrow, if you go for real research, you'll be asking many questions and answering to this. So that really inspire and come out the many research outputs and breakthroughs, research contributions after that. So anybody? So what is your answer? Yes or no, at least, or you can explore that. Can machine think? No one? Okay. So that means you are not listening or you are not interested or whatever maybe. So you can just unmute and say. So this is so only due to the pandemic we are separated, interacting virtually. Otherwise, you would have in the same conference room here in the universities and interacting. So next time we will make it really happen in person. So can machine think? Okay, since nobody is Oh, so I sorry, I could not see that chat box here. So what is the answer, Vivek, for this?
Some says no.
Oh, some says no. Okay, so we'll come to that. Right. So this question was posed by Alan Turing. So he's a London-based mathematician, researcher, and a pioneer of Turing machine and general purpose digital computer, etc. So he published a research article in Mind magazine 1950 entitled Computing Machinery and Intelligence. So if you could go through this article, this very interesting article. He says about thinking machine who can think and related activities. So this is the actual real starting point of the artificial intelligence. So if you could get a chance to read this article, it will be very useful for your understanding how the researchers in 1950s thought about the artificial intelligence and related activities. So computing machinery and intelligence. So whenever I ask this question to my research group here or the students interacted with me, some of them says that is it thinking or is it processing? While you listen to a process or you consider something doing by a computer, normally we don't think it is thinking or is it processing, right? Uh, and some people may interact like, how could you ever tell that a machine can think? As you said, some people in the chat box, they said no. Yes, they say that no, thinking is too complicated. So these are the answers I get normally from the students, those who really reply to this question. So some people may say that yes, machine can think in principle, but not necessarily the same as we do, human beings does normally. So these are some of the answers I compiled that I received from many students when I interact. So these questions are relevant. So, but still, if you could say that a machine by or an algorithm or a program prepared by IBM, which can defeat uh, the world chess champion Gary Kasparov in many times. Then, if you say that the playing chess is an intelligent game, or you require intelligence for playing chess, then if a machine could defeat your world champion human Gary Kasparov, then you could really say that you have to uh, appreciate the algorithm, or you have to say that this machine got some intelligence. Is it correct? So, so that is how we can say that the algorithm or the program is running on a machine which could play chess against a human and won the uh, uh, program, won the game, right? So, as I said, the um, suppose this programs or algorithms or machine can defeat human beings in some intelligent games, at least you have to uh, trust them and say that the machine got some intelligence in that. So you have many such applications or the games, whatever it may be, which can defeat humans in reasoning purpose type of thing. So the underlying thrust force behind every intelligent system is knowledge. So this is how we look into this. So suppose you want to build a machine which can act intelligently or which could perform reasoning process or to solve real life applications which really require knowledge, then the underlying thrust force behind that machine is knowledge. So what is knowledge? So you have to define knowledge at least this point of time. So whatever machine you require to make it intelligent, to make the system intelligent, require knowledge, right? So this is the knowledge pyramid structure normally we see. So it starting from the data. It is a raw fact and figures. You can put it as a data. You process it by a digital computer. Normally it will be named as information. And what is knowledge? So you know up to information. So a processed data is called information. So what is knowledge? So any idea? So how will you define knowledge? So you have seen many such type of knowledge around you. You are normally dealing with that in real life situations, scenarios, right? If I ask you a question like, which mode of transportation is useful in hill areas? Car, bus, or jeep? So what is your answer for that? At least you should say that. You can unmute and say. So I'm not able to see your chat box. So you can say, which mode of transportation is useful in hill areas? Car, bus, or jeep? Right? Yeah. Jeep. Okay. Right. So Ranjita, Joby, and other persons who are respond to that, thank you for your response. Right. Okay. So it is jeep. So how you got this answer? So your brain has uh, acted there, and you are respond to that answer by saying it is jeep. So have you ever uh, had an experience of driving jeep in hill areas? Maybe no, but still your brain says that this is useful in hill areas. This vehicle is more comfortable in riding in hilly areas, or even off-road trucking or driving process, right? So somehow you got this idea about, through your experience, your brain is recording all, and this has become a knowledge, right? Part of that. So and when I was asking the same question to another group of students while I was interacting in a seminar, they told that sir, we got this answer from the movie Brahmaram, right? uh, you also might have experienced that. Suppose you watch a movie or your videos, or you go there really, or somebody your experience in traveling through hill areas, somehow you are recording that. So it is a knowledge, right? So if I ask another question like, if what will happen if sodium or potassium you put in a beaker of water, so what will happen to that? So it explore. So similarly, you have many such knowledge. You are handling with knowledge, variety of knowledge in the real life scenarios, right? So if you are in a room temperature, I am giving a piece of ice cube in all of you, right? And ask you to write what you feel in a piece of paper. So, okay, you are in a room temperature. I am giving a piece of ice cube to each one of you and ask you to write what you feel. So you write, probably you write it as it's cold, right? So I compile everything, early answer from you, and coming to a conclusion that ice is cold, right? So this is some of the examples that you find in the real life scenarios. So a piece of information that helps in decision making is named as knowledge. A piece of information that helps in decision making can be named as knowledge. So this knowledge we need to incorporate the intelligent machines. This is the main task. So you have n number of mathematical models to incorporate human knowledge or whatever knowledge you have to the intelligent system. So as I said, the knowledge is the underlying thrust force of every intelligent systems. So you need to represent knowledge, incorporate knowledge in the machine in a different mathematical models, etc. So this is the main task of building intelligent machines. And what is intelligent? So after so suppose you take a example of medical diagnosing system. So if you want to help your medical practitioner or doctor to diagnose a particular disease, right? So you are creating a intelligent machine for that. So in that machine, you need to incorporate the human knowledge, doctor's knowledge, how he diagnoses a particular disease. So what are the test results he go for? What are the symptoms he analyze normally? While you examining a patient, what are the things, procedures they do normally? Everything we need to incorporate in the machine. So this is the challenge for you to build a intelligence system, and it is you have to understand that. So every intelligence can be made only for a narrow problem domain. We cannot generally make a system which can handle all your to solve all your problems. So it will be normally done to solve a particular problem, narrow problem domain. So what is intelligence? You know what is knowledge now? What is intelligence? So are you intelligent basically? Yes or no? Yes. Jofi, you are right. Yes, it's correct. You are intelligent. All human beings are intelligent. So what is intelligence really? So I say that yeah, okay. So intelligence is the ability to draw useful inferences from the available knowledge. It is your ability to draw useful inferences or your patterns, whatever it may be, reasoning from the available knowledge. So you got a knowledge base instead of database here. Intelligence system you got knowledge base, and ability to draw useful inferences from the available knowledge is uh, mm, uh, intelligence. So in the inaugural address from the Vice Chancellor, he was mentioning that suppose you want to build a precise, accurate, and scalable system, you listen to nature. So that was a statement he was giving while he saying about intelligence systems. So most of these intelligence systems and algorithms are biologically motivated. That is another important statement you have to listen. So most of the algorithms are inspired by human brain or whatever you see in the nature. So that is incorporated in the intelligence system. So to build intelligence system. So the ability to draw useful inferences from the available knowledge. So can you will you be able to incorporate that ability, intelligence to this particular system? That is the beautiful machine that is called the digital computers that you have in hand. So can you build an algorithm that? Can you write an algorithm for that? So that is the scenario. So wisdom you forget about at this point of time. This is the maturity of mind or something like that. So a lot of definitions are there, but still up to intelligence we are trying to incorporate in digital computers. So that is our main task of building intelligent systems with the help of machine learning and signal processing tools. So this we have already discussed, right? Knowledge and intelligence. So eras of computing, if you go in the timeline, you can say that we started from tabulating system era in the uh, long ago. So we started building electromechanical machines for getting tabulated something. So tabulating system era, we go tabulate uh, machines for tabulating something. Then you gone through the programmable system era. We got different type of programming systems where your programs are used to. Most of the time, we use our programming task for uh, scientific problem solving. Where suppose you have a problem, so suppose you solve it by yourself, it may take long time consuming, or if you do it yourself, it may have error prone. You may get a lot of errors. Suppose human beings are doing. So error prone or time consuming numerical computations are done by the digital computers very easily. So that was the era focused on. Now stuck to humans, why can't we use this machine for reasoning or intelligent computing? So this is the cognitive system era. So you are very lucky that you are studying this concept of computing in the cognitive system era. Instead of tabulating or programmable, that is forget about everything. Now you are in a cognitive system era. Everything taken away by the intelligence systems and algorithms, which is supporting to build to really solve your challenging real life problems, right? So I will tell you some classification. How will you say that the conventional programming differ from the cognitive system programming? Like, so you got an algorithm. Suppose I want to ask you to write a program to solve quadratic equation: a square plus bx plus c is equal to 0, right? So what you will do normally? Suppose ask you to write a program to solve a quadratic equation: a square plus bx plus c is equal to 0. So will you be able to write that algorithm for at least for algorithm for that? Yes, right. So I'll be moving little fast because I have to stop it by 3 o'clock. By that very important speaker will be available from 3 o'clock, right? So right. So plus or minus root of b square minus for ac by 2a. That is the equation you write for that. But still, suppose I ask you to write a program or algorithm to understand, to recognize face. Is it possible? Or speech recognition. Is it possible to write a algorithm for that? Or suppose you want to implement the share market trading or medical diagnosis. Or suppose we take an example of face recognition. So will you be able to write a mathematical equation, as I said, plus or minus b square minus 4ac by 2a, in the case of quadratic equation, will you be able to do that for a face recognition application? Suppose you want to build that. So you know that most of the mobile phones or cameras, they have this face recognition as a biometric. Yeah. Yeah. Sarita is saying no. Yes, correct. You will not be able to write a program as you said in the case of a conventional programming technique. So there is no mathematical equation to solve these real life applications. But still, machines are capable of doing, right? So how will you do that? So this is the machine learning algorithms that we are approaching. So how this machine learning from the samples, examples, whatever it may be. So altogether, it is a different approach to solve the real life applications, where I said in the case of face recognition. So there is no mathematical formula which can be used to solve, so that you can take the input and you apply to this and getting the output. This is not the conventional programming methods. You will not be able to solve this type of problems. So you find an n number of programs which normally deals with the knowledge and the intelligence, etc. You need a different type of approaches and algorithms, which is really want to implement the real life applications, which really want to process the knowledge. So human perception is very important. So humans have developed the highly sophisticated skill of sensing their environment and taking actions according to what they observe. Right? It is a changing environment. You are adaptively taking decisions. So you have a sophisticated skill for sensing the environment. Can a machine do that? So there comes the importance of learning. So this is how learning starts. Ability to improve one's behavior with experience, right? So this is the basics of learning. This is a human perception. So ability to improve your behavior with experience. Can a machine do that? Can an algorithm do that? Can your program can be adaptively respond to the changing environment, right? So we would like to give similar capability to machines. So this is the basics of machine learning. So this is the important. So as I said, this is all biologically motivated. In the initial stage, people were thinking, those who are working in the AI field, to mimic the human brain. So now it is not the case. So human brain has a lot of capabilities, but machine has another set of skills or capabilities. So we don't really want to mimic the human brain, but still we can have some algorithm which is really inspired by what is happening in the human brain, right? So this is machine learning scenario. So you can see that the conventional algorithms or programs, as I said in the case of uh, uh, solving a quadratic equation. So you will get a set of data inputs and you have a program. Then your computer will give you will execute your program and give you the output. So this is normal scenario you are familiar with. So this is the environment you are familiar with. But in the case of machine learning, the scenario is little different. You have data and we have input output samples. So you say that. So we have uh, supervised and unsupervised machine learning. We'll come to that later. But still, so in the case of supervised learning, you will require input output samples. So you give the data as input and this is the output. So this is another data set, this is the output. So you have n number of input output sample to the computer, right? Then the computer will generate the model out of that. So you suppose you want to recognize a face, as in the case of, as I said in the earlier example, suppose you have five individuals, your friend's face, a different photograph of your friend face, then you train the system that this is the set of images you are giving for person one, and this is the actual person name, and another set of samples for person two, and this is the person's name. Like that, you have five different set of uh, face samples given to the system, and you are saying that this set is corresponding to this class. Class means this particular individual. So like that, you are giving to the system, and the system, the learned output will be a model which can be used to test the unknown sample. Suppose you have a model ready, your mathematically your model that all classes given to the system, and if you get an unknown sample, unknown face photograph, then you give to the system, and system will be able to say that this is this person. So this is the concept. So building computer system that automatically improve the performance with experience. So this is the basic underlying idea about making machine learning programs. So that is what our interest is to how to make your own programming environment for doing such machine learning tasks. So as I said, this is the extension of that graphical representation. You have rules and data, and then you get traditional programming, you will get answers. Rules means your algorithm or a mathematical equation you have, then you have given the data, input data, then it will give the output. But in the case of machine learning, you will get the data and answers given to the computer. So you will get an input-output pair giving to that, and you will get a rule or a model out of that. Then you give data to this model, it will give some predictions. So this is the basics of machine learning you have. So you have a definition for this machine learning. So you can say that Arthur Samuel, so he was giving in 1959, and he was a pioneer in checkers game. He developed this game of checkers in computers. And he says that the field of study that gives computers the ability to learn without being explicitly programmed. That is important. So you don't want to explicitly program to learn. The algorithm itself take care of learning things. So you don't have a mathematical equation or explicitly you need to program that. So widely accepted definition of machine learning is by Tom Mitchell. It is in 1998 he proposed this definition. So most of the books you can see this definition for machine learning. Just like computer program is a computer program is said to learn from experience E with respect to some class of task. As I said, it will be in a small specific task domain. You will be defining that. You will define the experience E and performance measure P. You define all these things. You measure experience in terms of E and task T and performance measure P. If its performance is in at task T as measured by P improves with the experience E. So this is the definition. A computer program is said to be learned from experience C with respect to some class of task T and performance measure P if its performance at task T as measured by P improves with experience, right? So this is the concept of machine learning. So you can think of developing such algorithms. Why this machine learning important? So is there is any difference between the conventional programming, or you cannot do it by the conventional programming techniques will not be applied to the some task. That's what I said. So we will not be able to use this particular set of conventional programming algorithms will not be suitable for that. Is there any reason for that? So that's what you're saying. Some tasks cannot be defined well except by examples. So recognizing faces, we cannot define with a mathematical equation or something like that. But you can set example, except by examples, right? So, and another point is that relationship and correlation can be hidden in the within the large amount of data. Suppose you want to train a large amount of data, and the relationship and the correlation among the it will be hidden in that. So machine learning may be able to find this relationship and explore out of that. So that is another point. So environment changes over time. So we'll not be able to cope up with that in the case of traditional programming language. The amount of knowledge available about certain tasks might be too large for explicit encoding by humans. For example, medical diagnosis, as I said earlier. In the case of chess, you know that number of rules can be applied to a current chessboard position. Number of rules or the moves can be applied to a particular chessboard position at any point of time. So amount of knowledge available cannot be incorporated in a traditional programming techniques. So tasks may be too large for explicit encoding by humans. It is not possible. Suppose you write an algorithm for that to encode all this knowledge incorporated to that machine. So you need different type of algorithm for that. New knowledge about task is constantly being discovered. So suppose your machine is identifying new knowledge. How will you incorporate the machine to the algorithm itself, to the program itself? So it may be difficult to continuously redesign system by hand. So it is not possible. So automatically your algorithm should take care of all these changes or new knowledge to be generated by as part of your system. So you listen to this first. So as I said that there is a prediction function. You have a prediction function for that. You are extracting some features to identify certain objects, right? To representing the image, you got 3 images: apple, and tomato, and a cow. You suppose you want to extract the features and give to the prediction function. It should really spell out the object name. That is the scenario. So your conventional programming or algorithms will not be able to solve this. So you train your system with the different set of input output samples of all these objects, and the prediction function will give you the output while you give a unknown sample to this learned system, right? So this is the framework. So you got an output and you had a prediction function. You are extracting some features. So what features will you extract for an apple, which can be discriminated or classified from tomato, that you have to identify, right? So initial stage of machine learning, we have a feature extraction stage where you really extract features which may be a color, shape, or geometrical features, whatever it may be. You extract and give to the system, then you train. That was the scenario. Then the prediction function will predict it. So you have a training part of that. So suppose you extract features, so given training set of labeled samples, as I said, x1, y1, x2, y2, xn, yn. So x1 will be your input feature and yn will be the class associated with that. So you say that you extract some features from the sample for apple samples and give that this is apple, right? So then you go for the tomato, you extract some features and you say that this is tomato. You extract some features from the cow image and you say that this is cow. This is the training set, labeled examples. So you are going for a supervised learning. So, and this estimate the prediction function by minimizing the prediction error on the training set. This is what your training algorithm will do. So we'll come to the different type of training algorithm you have, supervised and unsupervised. So the prediction function will so you estimate the prediction function by minimizing the prediction error on the training set. So this is what you call it as training in machine learning. Then what is testing? Testing is nothing but you apply the function prediction function to a never before seen test example. You extract the same features that you extracted for the training set. Then the same features will be extracted from the test example x and output the predicted value y is equal to f of x. So your prediction function will apply on the text example feature, then you will get the desired output of that. So this is how the training and testing is happening in your machine learning concept. So this is nowhere in the conventional program methods. You cannot see this type of minimizing the prediction error and your prediction function will give you the output type of thing. So your learned system will have a learned prediction function which can perform better. So so you have the training samples, many samples of apples and pear and your other objects like tomatoes, cows, and sheep, etc., dogs, etc. So you extract the features out of that. So what are the features? It will be extracted by you. You define the feature set. Then your training labels will be used for training these features, and you got a learned model. So mathematically you will get a model. Suppose you come to the artificial neural network, I will tell you. So you have machine learning techniques, different techniques are there. So accordingly, you will get a learned model. So in the testing phase, you get the unknown sample of a object that is already given in the training phase. So you extract the same features that you have extracted for training. Then again, your learned model that you arrived out of your training process will give you the right prediction of the object. If your system is correctly learned, then you can say that this is the system will say that this is apple, right? As human beings, you can see this is apple. Your system will also predict that this is an apple. So this is how your system works. Okay, so you have supervised and unsupervised and semi-supervised learning and reinforcement learning. So I am not going to the this type of algorithms right now or concept of this. I will share you the slides to all the registered participants and your recorded videos of all these talks also. So you can refer to that in future. So this is an anonymous saying. If the only tool you have is a hammer, then every problem looks like a nail. So what the problem different type of problems we have identified, starting from the medical diagnosis to playing chess to share market trading to speech recognition to image recognition, object recognition, face recognition. So these all are different problems. So if the only tool you have is a hammer, then every problem looks like a nail. So you need different tools to solve this set of problems. So we have a set of soft computing. So we have collectively we call it called soft computing. It is coined by Lotfi A. Seda. So we say is a father of soft computing and fuzzy set, etc. He's saying that soft computing is an emerging approach to computing which parallels the remarkable ability of the human mind to reason and learn in an environment of uncertainty and imprecision. That is very important. So most of the time, your brain is taking decision based on the vague or confused or uncertain or imprecise input. So you can experience that. If I show only the lips of your favorite actor or actress, you can say that this is the actor. If I show only the eyes of your particular person, you can say that. If I listen to the voice of Amitabh Bachchan, you can say that this is Amitabh Bachchan. If you see a person from the behind, your friend walking away from the building, you are standing on the top of your building and say that this is the person. So these problems you are not giving your brain the actual input. So even with the vague or confused or fuzzy or imprecise, uncertain input, your system, your brain will be able to process correctly and give you the correct answer. Right? Can a machine do that? Right? So complex real-world problems require intelligent systems that combine soft computing techniques and methodologies from various sources. So we have n number of different approaches to solve all these real. Can we do that with your machine? Right? So these are some of the neural networks. As I said, this is a biologically inspired algorithm. So you know that this is the biological neuron. The information processing unit in your brain is the simplest or the most unit processing information processing unit in your brain is biological neuron, right? You know how it works: dendron, dendrites, axon, and axonize, etc. So similarly, we have we have this number of neurons in your brain. It is a biological. So we have a similar mathematical model called artificial neural network. So you know that, and I don't want to go into the into the biological aspects of that. You know that the input should be acquired by this neurons by the axons and axons, and you can say that it will be processed and it will be fired if it crosses some thresholds. So, like the brain, artificial neural network is a massively parallel collection of small and simple processing units where the interconnections from the large part of the network's intelligence. So you can see that this can be mathematically modeled. So perceptrons are nothing but it is a neuron. It's basically a single neuron model where you can get the inputs and weights associated with that. So that is the, suppose you say that your machine is learned, then this weight is representing the learned system, right? So there is a summation processes. You multiply the inputs. Suppose you have extracting a feature, right? X1, X2 up to Xn, and your perceptron will be connected to a summation processor. It is shown here in the figure, just like a sigma. And what you do, so there will be a bias also. You multiply your input with the corresponding weights associated with that. Then you process it. Then it will be passed through a activation function. This is called adjustable threshold U. Then the neuron will fire, or the perceptron will give you the output. So this is the simple perceptron model which can be used for classifying linearly separable data. So this is how it works. So learning is the process of modifying the values of weight and its threshold. You can modify the input, you cannot change, the output will be there. So then in between you have weights associated with each connection to the summation module, and there will be a adjustable threshold value also. So suppose you take the input x1, x2, xn, and you have connection weights w1, w2, wn, then your g of x will be W1 x1 plus W2 x2 up to W1 xn, that is sigma I is equal to 1 to n Wi xi. So your perceptron fires if the weighted sum, that is your g of x, is greater than 0, otherwise it will not fire, give any output. So this is the scenario. So let us take this example of pattern classification. So you want to classify two flowers, jasmine and lotus, right? So you extract some features out of that. So what are features? Color features, smell, everything you can extract. But for the ease of computation, or to explain to this to you, I am taking the petal length and width as the features. X1 is the length and X2 is the width of the petal of each flower. I selected 50 samples of jasmine and 50 samples of lotus. I extracted the features X1 and X2, which is corresponding to length and width of the petal. And I plotted the graph here. You can say that the blue graph will be represented for which flower? If I extracted this, which flower? If you are listening to me, so definitely you'll be able to answer it. So blue dots will be representing which samples of flower? Which flower? And red will be which one? Tell me. Right? Anyone is saying that? Blue will be which flower? Jasmine or lotus? Feature 1 is your length and feature 2 is the width of the petal. Anyone from the participants? You'll be able to say that? So nobody is interact. Okay. So yes, yeah, blue will be jasmine. Thank you. Yeah. So because they have a smaller width and height, right? So it will be like, so how will you classify that? So you say that your g of x, you calculate this sum of weighted sum of your input and the weight, and g of x is equal to 1 if g of output of x, O of x is 1 if g of x is greater than 0. Suppose you solve, you have only two inputs x1 and x2. For this you will get g of x is equal to w0 plus w1 x1 plus w2 x2. You carefully listen to this equation. You can say this is the equation for straight line. If you solve the equation g of x is 0, we get the equation for a straight line, definitely. Then you identify the slope of that. Then we can say that, so you will get a straight line. So you say that if all the samples, suppose you get an unknown sample, if it is below that slope, you can say that this is jasmine, and above that this is lotus. So this is how the program, the perceptron classified. These are linearly separable samples are there, right? So you can see the activation functions. You can have here you have only one threshold function, but instead of that you can have multiple activation functions, different activation functions. So the g of x is usually processed by activation function f to produce the neuron's output signal. That is, it may say that O of x is equal to f of g of x. So that is called the perceptron. You can have this type of step function or sigmoidal function or bipolar continuous sigmoidal, whatever it may be. So you can see the output will be varied like that. In the step function, you will get -1, 0, or +1. In the first function, you can say that it will be giving 0 and +1. And the sigmoidal function, you will get the continuous varies from 0 to +1, right? Bipolar continuous, you will get -1 to 1, or continuous values. So this is how. So you can generate normal OR and NOT gate from using the this type of perceptrons, and you have multi-layer perceptrons where you get to solve. Suppose you take the XOR problem, you know that these are the two classes you have. So you are getting 0 output for 0 0 input, and 1 1 input you will get 0. So this is one class, and another class for 0 1 and 1 0 you will get output as 1. So you will not be able to classify this with a single straight line. So perceptron models, if you see, you can classify these two classes based on a straight line. But in the case of XOR problem, if you say, you will not be able to classify this in a single straight line. You have two straight lines. So this is not linearly separable problem. There you really require multiple hidden layers. Multiple layers. So this is a two-layer perceptron, multi-layer perceptron. We call it a multi-layer perceptron. In the previous case, you have seen that this is only a single layer perceptron here. So what is that? This is a single layer perceptron. If you have multiple layer here, you can say that you can solve problems for non-linearly separable, which cannot be solved or classified based on a single value. So this input output from the perceptron will be given to the output. You can see some weights associated with that. These all are hand-coded weights, right? This is to solve the XOR problem. We have hand-coded the weight. This weight can be automatically generated by the machine? There comes the importance of your learning algorithm, right? Suppose you give input and output, then the algorithm itself will generate the weight automatically. That is how your backpropagation learning algorithm and everything is working out of it. So you see, this is the input, and you have associated weight of that, your activation function. What to your summation, you will multiply the input with the corresponding weight, and you pass to this function. Here it is 1 by 1 plus 0 to here e to the power minus x. This is the activation function you are using, sigmoidal function, which can take the values 0 to 1, continuous values from 0 to 1, right? So then you will get the output of that. So then you, in the training set, what do you see? You give the training set to the initial stage. Your weights will be random weights. You set the weight as random weights in the initial stage. Then you give the input output to the neuron. So you have given input and you are saying that your class is 0, but you got an actual output of 0.8. Then the next stage, what you do, there is an error. So you have to minimize that error. What you do for minimizing the error, you adjust the weight in between. Your algorithm will adjust the weight in between, right? Accordingly, you give another input output pair, epoch. You give that. Then accordingly, you will find the output. So there is a improvisation in the output. That is, the error is less than your previous one. Now it is minus 0.1. Previously it was 2, right? So again you adjust the weight in between. You give the same thing, input out different, you find the error, then you minimize the error. So this is back propagation of error. So you got a beautiful algorithm for multi-layer perceptron 2 is the error back propagation algorithm. So you can refer to that. So repeat this process, and algorithms for adjustment are designed to make changes that will reduce the error, right? So it is how it is happening. You see how it is taking place in the decision boundary perspective. So you have a decision boundary in the classification problem, a straight line. Suppose your real life applications, just like face recognition, speech, will not get the straight line linear classifier. You may have the patterns here and there. So initial random base, suppose your decision boundaries like that. Your algorithm, after training instances, you are giving input output pairs and adjusting the weights, then your decision boundary changes. See, now it is again changes. You are training, your system is learning something. Then again it is changing. You are giving another set of input output pair and adjusting the weight. Again, decision boundary is changing. You see, again it is changing. You are learning. Finally, your learned system there, you can see that decision boundary which can classify these two set of patterns, right? So classifying this, eventually it will happen that. So this is how the decision boundary is changing while you adjusting the weight in the neural network that you are giving. So so you can see this how it is happening. So in the supervised learning process, you give the input output base. So here we are using an example for fake news classification. How will you identify fake news and the legitimate one? Suppose you take the fake news here. So again, you have legitimate one from different source of news portals or blogs or social media. You give the two set of weights. You know that this is fake and this is legitimate one. Okay, so different set of website you are getting the fake and the legitimate one. Then your machine learning algorithm, supervised algorithm, you pass to that, you extract some features out of that and training that. Then finally you have model and you're saying that this is fake and this is legitimate one. This is how happening in the case of supervised learning. So what kind of features you are extracting is very important. So to learn the model, so that is the challenge out of that. So you have to extract features in the initial stage of algorithm. So they were using extracting features out of that. And in the case of and what kind of learning models you require, actually which algorithm you use for, as I said, in the case of error back propagation, for in the case of multi-layer perceptron, you have n number of learning algorithms you can use based on the architecture you have. So this is how the supervised learning mechanism is. This is the one of such work happening in the university campus, the department, in association with Queen's University. Professor Deepak sir will talk to you in the coming session in detail about the collaboration and all. So in the case of unsupervised, you don't know. The large majority of works treat fake news identification as a anomaly detection. So you see, you have a set of news, you don't know whether it is legitimate one or it is not labeled actually. It is not a labeled data. Then you directly pass to your unsupervised learning algorithm. It will say that this is legitimate and this is actually the fake news based on the features. It automatically identifies. There is no supervised inputs. That is, input output pairs are not given to that. So the learn the character on nature of the documents as a statistical model. It will learn as a statistical model and identify those that deviate from the general character and label those as fake news. So there will be a general character to be learned for the documents, and if it is deviate from the general character or the features, then it will be identified as fake news, etc. So this is unsupervised learning plans. So I don't want to go to that. You can refer to this in future. This is a computational perspective of single layer, two layer, and multi-layer perceptrons and the different problem set, how it classifies and all. So this is the taxonomy of feed-forward neural networks and recurrent networks that we have to build the systems. So formal learning algorithm. So I'll stop this here. So because suppose you have g of x, this indicates how far a given input vector x lies from the decision surface, right? So how far the input vector x lies from the decision surface. You have seen the decision surface or decision boundary. How good a set of weights are. Okay. So I think our next speaker is already here. I'll take another 5 minutes and wind up. So, and let W be the weight vector. So you have weight vector here, X be the subset of the training set that misclassified by the current set of weights. So you have a set X be the subset of training instances misclassified by the current set of weights. So you define a perceptron criterion function J of W is the sum of the distances of the misclassified input vector from the decision surface. That you call it as a criterion function, and to get the better weight set, we would like to reduce the this criterion function, that minimizing JW, so you can have gradient descent or whatever algorithm you use for that. So this is how the formal learning algorithms work normally in the case of machine learning. So definitely from 1940s, you can see that non-linear threshold gate, the McCulloch's and Pitts model started in 1943 as a connectionist model for machine learning. And in, you know that cybernetics is an interaction between man and machine. How the control and communication between man and machine is defined in the cybernetics. It is a branch of computer science started in 1940s to 1960s, and the Rosenblatt introduced the perceptron learning model in 1958. That was another. This is called historical wave of AI research. You can see many up and downs. So down you can see this is the AI winter, but now on you can see that 2010 onwards you can see it's a huge hike in the curve, hike in the curve. So you can see that now you are very lucky to study this topic while you have the peak of machine learning. So AI winter, you can see many up and downs are there. So after cybernetics and introduction of perceptron, there will be a down in AI research. Then 80s onwards, 86 onwards, there is a connection system started and error back propagation proposed by Hart. Then you see now you have deep learning to greedy layer wise pre learning. Many people are working on that. Jeffrey Hinton, Bengio, and Rensato. So if you go to their work, you can see that how this deep learning is taking away in that learning perceptron learning model. That is a multi-layer perceptron learning model, like backpropagation of errors. You can see that. You can refer to this type of article. So you see. So these are the deep learning researchers that we normally follow. Jeffrey Hinton. You can see it's a Google and the University of Toronto he's working with, and Bengio. You can go through this his their biography and see how they have contributed to this particular branch of computing sciences, right? And definitely, I know Andrew Ng's tutorials you might have listened to previously, and you can go to the Coursera and deeplearning.ai system. So he have given n number of lectures and learning tutorials and MOOC programs for understanding the concepts of deep learning architecture, etc. So I don't want to prolong much. So how deep learning is coming? So as I said, the feature engineering was was done by humanly, or the program will. So we have to extract the features from the input, and you are giving to the classifier in the initial stages. Feature extraction and feature engineering was done explicitly in that type of things. But in the case of deep learning, the feature engineering or feature extraction and classification process are blended together, and it is automatically taking care of the algorithms. That is the core difference between these machine learning approaches that we have in the conventional machine learning with the multi-layer perceptron and deep learning algorithms. So I don't want to give. So this you can see that in the input layer. So this is the input. Though hidden layer one, it will be extracting the features just like edges and combination of edges and object models. So different feature engineering. So computers, what computers see can be learned from hierarchy of features directly from data. So this is can be learned the hierarchy of features directly from the data. So this is the concept behind the deep neural networks, so deep learning algorithms. So I don't want to see this. So you will get definitely you will get all this ideas from the coming speech sessions, and definitely this type of works are this is for content-based image retrieval, scene analysis. Suppose you say this is a factory environment, this is a swimming pool. Can your machine do that? Object recognition, identifying different type of objects, even though the features are different, still you will be able to do that. So ImageNet. So some students might have gone through this. This is a huge, large database of images which can be used for deep learning algorithms as input. NLP to cognitive computing. So this is a tour picture of our department. Suppose you say that face recognition is something different. You can say that this is Vivek in this picture, this is Lajish, and this is somebody else and all. But still, if your machine could do say system, I don't want to do that. So conventional keyword spotting model will not give you the right answer sometimes. So suppose you are talking about Portugal celebrated the 400th anniversary of the explorers' annual arrival in India. So that is the question. And supporting evidence, suppose you go for the keyword spotting, so you may end up that your answer is Gary, because he arrived in India after he celebrated his anniversary in Portugal, right? So the answer will be different. So in a question answering system, but in the case of this is the guy who have given by the system. But supporting evidences, if you correctly go through this, so knowledge-based systems, and so I don't want to. So definitely, you will answer will be Vasco da Gama. Suppose you do the correct digging of knowledge from this type of question answering system. So the system is matured. The algorithms are matured to give you the correct answer based on different evidences. That. So this is only happening because of the deep learning architecture here. So I skip this slides. So most of the machine learning research happening in this department is based on the speech and image processing. Definitely, this speech is our core area. Malayalam speech recognition, keyword spotting is recently done, and the synthesis of speech based on multimodal models we have analyzed. So you can collaborate with this. So I don't want, so I'll share you the slides. So you can go through some of the works that we have doing here. And suppose you really want to collaborate with this, we are happy to help you out coming out of all this type of this thing. So next speaker is ready. So we have some collaborations and research outputs we have generated. This is another paper published we together on emotion cognizance improves the health fake news detection, and Anu and Professor Deepak Padmanabhan from Queen's University, they have contributed to this paper. So I'm not going to the details of this, but still we have a project called Break the New Fake in the department. So you can visit this website and contribute to the fake news that you identify from your surroundings. You can post to this. We will be able to use it in our training or their system to make it improve the performance. Okay, so this is another work done by our research scholar here, Manjari, on deep learning based digital image forensics. So very promising work that we are getting some good results of also. So what we are doing is we are classifying the computer graphics image, photographic image, and the GAN image, which is generated by the deep neural networks called GAN. So will you be able to do, your machine can classify the real photographic images and the computer generated images and GAN images. So we are working on that. Another work that we have. So these are the the paintings that I have shared during my talk. So this is generated by the machine called Aaron, proposed by or constructed by Harold Cohen. He is a British-born artist who was noted as a creator of Aaron machine. So if you say that this machine got some intelligence, that is how it is generating beautiful paintings like this. So this is another work that we had done long back. So it is a robotic arm which can take orders in Malayalam. So it will say Valathote, Edathote. So it will move just like that. 8 Malayalam orders it will take, and we were working on this particular project, and Dr. Sunil from Kannur University also contributed to this work, and it is displayed in the Kerala Science Congress and got a lot of media attention long back. So that is my views on this. So thank you very much for your patient listening. Definitely, you can also join part of our research journey here in the Department of Computer Science. We're happy to help you out. So we have a strong Department of Mathematics and Statistics associated with the School of Mathematical and Computation Science. So this is a strong 3 pillars of machine learning and data analytics here: computer science and statistics and mathematics. Definitely, we have many researchers across the globe supporting us, including Dr. Deepak Padmanabhan. He is waiting for the next session. Sorry that I have taken 10 minutes of his time. Definitely, he'll be looking the AI in a different angle. So he'll be very promising researcher, and he is guiding us all the way. He is a mentor to our team, the entire Calicut research team from the Department of Computer. Since we have or any clarifications we get, I can listen to your queries. Yeah. Any questions or discussions if you want? I can take offline also. So I'm available all the time here. So you can mail me also. Suppose you want to connect it to the Department of Computer Science and research scholars and the faculty members here. Definitely, you are most welcome. So, any queries? Okay. So I stop here because I don't want to wait the next speaker a long time. So thank you very much for your patient listening. So I think you can definitely connect it to the researchers here, and the department will definitely offer you a collaborative system. We can connect to many researchers, research groups, and promising researchers working in this area, and you will be benefited out of that. So thank you so much. So I stop here.
Thank you, sir. Thank you for the wonderful insight into the different areas of machine learning. Now we are heading towards the final session for today. It will be handled by our eminent resource person, Dr. Deepak Padmanabhan. He is an associate professor of computer science at Queen's University, Belfast, and adjunct faculty at IIT Madras. He has authored 100 plus papers, 12 plus patents, authored 3 books in various areas of data analytics and artificial intelligence. His publications include top-tier avenues in artificial intelligence, natural language processing, information retrieval, data analytics, and other allied areas. His current interests are on fairness or ethical artificial intelligence and machine learning, particularly focusing on approaching questions of AI fairness from a philosophically informed perspective. He has a keen interest in public communication of science and has authored several popular media articles on the politics and ethics of technology. During the course of his academic career, he has been an investigator on successful funding applications or of a huge amount, graduated 3 PhDs, and developed a course on fairness in machine learning. He's a senior member of the IEEE and the ACM and a fellow of the UK Higher Education Authority. In the coming session, Fairness in AI, a general introduction, he will be talking about, or at a high level, AI applications of implicit assumptions that go into data-driven artificial intelligence. And I think we are lucky enough to have Dr. Deepak Padmanabhan as our mentor at University of Calicut Computer Science Department. And I proudly welcome you, sir, to this session to interact with the participants of this webinar on advanced machine learning and signal processing. Welcome, sir.
Thank you. Thank you very much, Dr. Reshma. Am I audible? All right.
Yes.
Yeah. Okay. Let me just share my. Okay. So on the slide is the title slide visible? Can you see the transitions? Okay. 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 Fine. Let me just see whether the transitions are visible. So now there is no image, right? What you can see. Are the transitions visible now? I'm just doing a few clicks. No. The transitions are visible, right? I mean, I'm just going through. Are the transitions visible? Okay. Okay, so I'll just go to the title slide. Yeah, thank you very much. And I think thanks very much, Reshma, and as well as earlier, I think a little bit of introduction to my interaction. I mean, it's been wonderful collaborating with the University of Calicut Computer Science for the last several years now, and with Lajish and his team, and I hope that this will lead to further results and outputs, etc. Yeah, so the title of my talk today is Fairness in AI, a gentle introduction. So this is basically a non-technical introduction to fairness in AI. Even if you don't have any sort of background in machine learning or AI, you should be able to follow this without any problem. But I know that most of you have a background, so that's even better. Let's start with a very quick example. I mean, this is like a very basic example of data-driven AI. So you start with, I mean, this is an illustration of classification. You have training data. I hope I just want to make sure that the transitions are visible because currently I hope you can see these two images and the associated captions, right?
Yes, sir. Yes, sir.
Yeah.
But your audio is little feeble, so if you could increase
audio is
that.
feeble, is it? Okay, let me just see just a second.
Otherwise, it is fine, sir.
Okay. It's an external mic. So just keeping the mic closer now. Yeah. I hope it'll be all right. I mean, if at all it becomes very feeble, let me know. Okay. Then
No, sir. Now it is fine.
Yeah. So the training data now often contains pairs of objects. The first one is the data itself, is the data object itself, and the second one is its label. And what machine learning does is that it takes in, or classification oriented machine learning does, is that it takes in these kinds of pairs. There is data object label, that kind of pairs, and then builds a statistical model. And this statistical model is able to capture some of the correlations between the patterns in the data and the labels. Okay, and that is captured and kept within the statistical model. And why is it kept within the statistical model? In order to do further downstream decision making. For example, if you have an image if you have a new image that was not present in the training set, so you want to know that whether it is suspicious or non-suspicious, then what you might do is you might feed it into the statistical model, and there will be a decision procedure which will take the statistical model and determine whether the patterns in the statistical model are able to vouch for this image as suspicious, or whether they would regard it as non-suspicious, and then you will have a label associated with it. This is the very simple way, very simple illustration of how statistical machine learning would work, especially within a classification scenario. So when you look at data science and AI, data science and machine learning has been around for several years, and I think towards the end, Dr. Lajish's slides also showed you how AI and machine learning have progressed for the last 7 or 8 decades. So during the initial days of machine learning, and I suppose most of you are from India and so on. So you might remember that 20 years back, the predominant job in the IT sector at that time was medical transcription, which was about taking prescriptions from doctors, and the doctors order prescriptions sitting in the US or elsewhere in the Western world, and then sent it over to India. And then you look through them and identify what is written there, right? And you enter it into an electronic format. And this is a mundane activity. Nobody used to like that activity. I had several friends of mine who used to work in data entry, medical transcription kind of fields. They never used to like that activity, but they just needed to do that in order to get some earnings, right? So it was a mundane activity, and that was being largely automated to a large extent by machine learning. And one thing to look at is, it's kind of curiously interesting that the actual work that was done by these people 20 years back actually probably formed the training data for the machine learning model in order to automate those very tasks. So in a way, and when you're doing some of these kinds of labor-intensive tasks, you're creating data to learn a machine learning model, which will eventually displace you from the task itself. So there is an interesting class kind of analysis over there. Classes, and I'm talking about, we had this image taken from CCTV footages and regarding them as suspicious or non-suspicious. And wherever something is regarded as suspicious, you can think of that. You can think of that picture as a map of a city where there are cameras installed, CCTV cameras installed, and whenever a CCTV camera gives out a suspicious image, suspicious as judged by the machine learning, it puts a red square around it. Okay, so these are areas of suspicious activity, and what you might decide is to say that you might send some of these police patrols there, and the whole intent is framed in such a way as to sound very appealing. It is meant to say that we would like to catch the crime even before it happens. So police forces are about addressing the crime after it happens. Whereas here you are saying that you would use machine learning in order to look at the crime, in order to prevent the crime before it happens. And this is kind of problematic from a jurisprudence perspective, from a legal philosophy perspective, because the typical legal philosophy is that the typical jurisprudence assumption is that you are innocent until you are proven guilty. Here, somebody knocks at your door and says that, okay, our CCTV footage has shown that there is some suspicious activity here. Are you involved in any of those? I mean, that is almost like putting the burden on you to prove that you are innocent, as compared to the default assumption where you are generally assumed to be innocent unless you are proven guilty. So predictive policing is a very different flavor of task. And predictive policing ensures or involves making substantive decisions affecting humans. And this is not just predictive policing. Predictive policing is just one example of that. There are plenty of these kinds of tasks. So we have moved from automation of mundane tasks in order to towards making substantive decisions affecting humans. And there is also another kind of movement as you go from this task, as you go from the left hand side to the right hand side. For example, if you look at the left hand side thing, it says winter is here. Right? I mean, there is no question about interpreting it in a different way. Winter is here is interpreted as winter is here, and if somebody transcribes it as winter is there, then it is meant to be incorrect. It will be regarded as incorrect. Whereas in this predictive policing scenario, there is no such thing as correct or incorrect. It is entirely up to human judgment as to whether a pattern should be regarded as suspicious or non-suspicious. So here you're automating a human judgment-oriented task as compared to just a pattern-oriented task, a pattern transcription-oriented task to machines. And this has significant social implications, if you think of it that way. So let us look at some of the use cases of AI these days. And it's not just predictive policing. Predictive policing is just one of those things. So here we can see about a kind of a use case where it is about identifying skin cancer, determining whether a particular skin lesion is malignant or not, is cancerous or not. And that is something that you can do by taking an image and then feeding it into a machine learning model, which has been trained over historical records, historical images of skin lesions, which are labeled as either cancerous or not cancerous. And as you can see here, you're already talking about dermatologist level classification of skin cancer with deep neural networks. And this is 2017. And this is and skin cancer determination from skin lesions is kind of a very interesting scenario because it does not involve any sort of context. So if I go to the doctor with a cough, then they would ask me various things like, did you go out? Did you get wet in the rain? Did you eat something which was unusual? Did you drink something cold, etc.? All sorts of things. Whereas skin lesions determining cancer is just a context-free kind of thing, in the sense that you look at the image and then identify whether, and that is the way if humans do it, that is the way dermatologists do it, and that is the way machine learning can also do it. Whereas if you have a lot of context, it's very difficult to capture these contexts and train a machine learning model. So that is kind of giving you a perspective about how what is a domain of application of machine learning which is much more favorable to it as compared to which is not so favorable to it. The other thing that I have here is about predictive policing again, but it's about an Indian use case. So as early as in 2015, the Delhi police made public its intention to use predictive policing tools, crime mapping, analytics, and prevention system. So it's called CMAPS. So predictive policing is not a Western phenomenon at all. It is there in our streets, in our midst. And the thing about this is law enforcement and policing is generally regarded as a public sector activity. In the sense it is managed by the government, it is totally run by the government. Whereas the moment you talk about taking some predictive policing tools, and these are typically private vendors, and using them in kind of law enforcement, you are opening up a window of privatization of a traditional public sector thing as well. And thereby, you also bring in notions of profiteering, you also bring in kind of notions of libertarian politics, etc., through that kind of a mechanism. Because you don't have a mechanism to scrutinize the training data which is held within the private sector entity, which is producing this machine learning model, right? You can only use it. You can scrutinize it by means of setting different inputs, looking at the outputs, etc. But you actually don't know about how it was trained. It might have been trained in a very biased way. So when you talk about machine learning, it is sometimes easy to think of very unusual circumstances where it could be used. For example, let us say that you want to do population estimation for a census information, for census records. So what you might want to do is send a person to each door, knock on the door, ask them how many people are there, and so on and so forth. I mean, we have census every 10 minutes, right? 2021 is the last one, not too far away. Basically, if you want to do a periodic census where you don't have the capacity to visit every door, what you might do is you might take a picture and just cover the people in that locality, and then take several of these pictures. Now you have a picture followed by a number, which is the number of people in the locality covered by the picture, and now you have an input-output data there, right? And if you put a sufficient amount of them, and you train a machine learning model, and now you have a different picture, and it will be able to tell you whether how many people are living in it. So let's look at some of the implicit assumptions that go into data-driven AI. So the first thing is, it is about codifying the past. It is about saying that patterns from training data are useful to make decisions and test data. And one should look at the temporal relationship between training data and test data. Training data is historical. You look at CCTV images from the last month, from the last year, etc. take a sample and subject it to human labeling and train a machine learning model. Training data comes from training data is already taken place. Whereas test data is in the future. Test data is coming up after the model is deployed. So the fundamental assumption here is that history repeats itself. Or to say it in a more technical way, it is to say that historical patterns and correlations are useful to make decisions about the future. The problem here is that history sometimes doesn't repeat itself. History sometimes, there was also a quote by Mark Twain who says that history doesn't quite repeat itself, but it does rhyme. And actually, I should correct myself and say that the fundamental assumption in machine learning is to say that history rhymes, because it doesn't really capture all these images and learn what it is in. So, but it can actually make sense of new data as well. So it actually captures patterns, and this capturing of patterns is essentially about capturing the rhyme within the historical patterns. But the problem here is that when you're making decisions using this kind of an assumption, it is sometimes not valid. For example, let us say that you use CCTV footages and identify some patterns that are problematic, and then install them in the AI-driven CCTV cameras. Now, these criminals might actually understand that these patterns are already captured. So they might actually say that they might actually do a different kind of pattern in order to do the crime. So that pattern is no longer valid because it's no longer used by criminals, right? So in that sense, the ML could actually influence the situation, influence the scenario in which it is applied. And this is the case of several kind of this is the case of several kinds of technologies. There is also a kind of thought here, which I might as well say here. I mean, the phrase is called technological determinism, which says that technology has to some extent a capability to determine how the society functions. And this comes from largely the Marxist school of thinking and so on. But you can look it up. I mean, it's a very interesting treatise on how technology can influence the body of research around technological determinism is very interesting. The other thing about AI is about generalization. So you're trying to generalize from historical data. And when you generalize from historical data, there is a very interesting thing here. I'll just go through all the things here. So let us say that you're trying to capture some patterns and store it in some information repository, store it as a statistical model. Let us say that there are two categories of people who behave differently, okay, in the population. Let's call them the majority category and the minority category. The majority category people have, let's say, 10 different behaviors, and the minority category also has 10 different behaviors. Now, your model is a parametric model. It can only store 10 behaviors in total. And how do you decide which 10 is to be stored? You have 10 from the majority, 10 from the minority. You have 20, out of which you need to choose 10 to store. How do you choose the 10 to store? One way to choose it, or the predominant way of choosing the 10 items to be stored, is to say that you will store the patterns in such a way that the accuracy is maximized over the entire population. So the number of correct decisions that you make over the entire population is maximized. So if you store just the 10 patterns on the majority, you might make correct decisions on the majority, which might be 70%, right? So 70% accuracy. And if you store 10 patterns on the minority, you might make correct decisions for the minority, which might be 30%. So you have an implicit preference in order to store more patterns on the majority. So eventually, when you choose 10 patterns, it might be 8 patterns on the majority and 3 patterns on the minority. So this parametric models and their training process, which uses a utilitarian kind of way of identifying which patterns are to be stored, is heavily limited and is heavily anti-minority as well. So in the sense, majority patterns would be well represented and some minority patterns might be totally disregarded. So machine learning or parametric models in machine learning, which are learned using a utilitarian method, which is to maximize the accuracy over the entire data, or could be argued as inherently anti-minority, right? So there is an inherent anti-minority component, and this is kind of quite interesting because, for example, if you just innocently train your data, train your model over the entire data, you might end up getting a very majoritarian kind of viewpoint. And that is typical, right? I mean, in the sense, like if you're talking about the media and so on, they want to reflect the mainstream. The mainstream is correlated to the majority as well. So what is mainstream? നമ്മൾ മുഖ്യധാര എന്നൊക്കെ പറയുന്നത് മുഖ്യധാര അഭിപ്രായങ്ങൾ എന്ന് പറയുന്നത് എപ്പോഴും that's always correlated with the majority. Sorry, I think most of you speak Malayalam, so just switch a little bit. But, yeah. So when you talk about data distribution, the data distribution is also an interesting thing. The fundamental point here is that when you learn a diagnostic model based on predominantly male data, the statistical model will perform better for males, and that is because the models get better when they're trained over larger amounts of data. So let us say that you have a person sitting next to you in the office, and you know that the person comes in at 10 o'clock in the morning. And let us say that you joined the office only yesterday, and you find that person came at 10 o'clock. Can you infer that the person will always come at 10 o'clock? You cannot, right? But if you've sat next to the person for a year, and that person is always coming at 10 o'clock, you can think of that as a behavioral trait for that person. So when you talk about these kinds of behavioral traits and identifying behavioral traits, it is about getting more and more data. Your inferences become much more robust when you have a lot more data than if you have less data. So if you want AI to perform fairly over demographic groups, we need to ensure fair data distribution as well. And this is often neglected in the internet to use all the data that is available. Here, I'll just show you the face recognition accuracy. So some of these big software vendors and their machine learning models for face recognition. So as you can see, Microsoft has an accuracy deficit of 8.1%. So it is able to identify male faces at an accuracy of 8.1% higher than what it can identify female faces from. So this is a significant problem, and where does this problem come from? You can look at this, right? You can think about the socio-political context around. Most of these AI algorithms are built from the Silicon Valley, and the Silicon Valley tech population is predominantly male, predominantly Western, predominantly young, predominantly educated, predominantly coming from democratic societies, and so on and so forth. So they bring with them a sort of way of thinking, and also the predominant male aspect brings with them a kind of easy affordance to get male data. So if they run a crowdsourcing kind of method there in order to collect some face information, they might end up collecting a lot more male data. And if that is the case, then what implicitly happens is you have let's say that you have 1,000 male faces and 500 female faces. What do? If for sake of accuracy, do you throw away the 500 male faces, or do you use everything? There is once again a utilitarian kind of thing that you use all the data that is available to you. You have spent your money crowdsourcing this information, so might as well use it, right? So, so that kind of a logic brings in these kinds of significant disparities in terms of accuracies. For example, female subjects have an accuracy, sometimes the accuracy deficit is around 20 percentage points. Sometimes we often listen when you talk about bias. We often listen to views from various kinds of media publications, etc. They often tend to talk about the data, right? They say that the data set is biased, so so this algorithm outputs are also biased, and that is in a way implicating the data collection process more than the algorithm design. In some way, that is about relinquishing the algorithm designer from the responsibility of the bias in its operation, in the operation of the algorithm that he or she, of most of it's a he has built on, right? So, so the thing here is, I mean, if you focus on the data, you are tending to use an assumption that holds the algorithm designer very innocent. This is a significant problem because there is a significant bias component that could come from the design of the algorithm itself. The statistical model design is inevitably based on assumptions as well. The assumptions could be of various kinds. For example, decision trees might make use of an assumption that objects of a class can be identified through a sequence of attribute-wise positions. And that might not work very well when you want to do a special kind of treatment for a particular kind of intervention. Let us say that you're talking about infant mortality, right? And within the Kerala context, we know that infant deaths are often reported within Adivasi kind of community. So if you want to do something specific to a particular community, to a malnourished community within within the Adivasi regions, and within maybe SC/ST kind of categories when you look at the caste categories, and within the lower income class and so on. So you want to do something specific to them. And decision trees want to use the sequence of attribute-based decisions at a global level, and they might not be able to do justice to this little small population, which requires some kind of special treatment. And when you talk about SPMs, you're talking about linear separability within a source and attribute space. And when you use CNNs, you're essentially saying that localized patterns are important. And when you use LSTM or RNN, if you're not familiar with LSTM or RNN, no problem at all. But if you're familiar with it, you can of course understand and appreciate this better. LSTM and RNNs basically come with an assumption that sequential patterns are much more important. So the question, there is another question: do these assumptions apply equally well to different demographic groups? And that is an often neglected question. That is never even addressed in the time. So the point that I want to make here is that designing algorithms that are used to make substantive decisions affecting humans is a political activity. And you should be conscious about the political underpinnings of these when you're doing that kind of algorithm design. If you're designing algorithms for maybe handwriting recognition, maybe that's not so important, because I mean for some handwritings, maybe for people with Parkinson's, the handwriting is not as legible, and you might be giving a low accuracy term. That causes a problem. That causes a real problem, because I mean Parkinson's people might have the data recorded incorrectly, etc. All of these kinds of issues. But the problem is that when you're making decisions about humans, and when you talk about decisions affecting humans, many times you make decisions that label particular humans, or label particular communities, or label particular locations with a particular label. For example, CCTV footages are about labeling a particular location as suspicious in that particular point of time. It is also inherently putting that label onto the people that are involved within that image, right? So, and many times we talk about labeling humans, right? For example, within the India context, when you have things like the Citizenship Amendment Act and so on, you have a mechanism where you label individual people as D, I think, which means that it was it was well, I don't know what it means, but it's some form of suspiciousness label. When you're talking about decision making affecting humans, and it needs to be heavily seen from a political lens, is what I'm trying to argue here. I have here an excerpt from the Ethics of Algorithms Mapping the Debate. Algorithms are inescapably value-laden. Operational parameters are specified by developers and configured by users with desired outcomes in mind that privilege some values and interests over others. At the same time, operation within accepted parameters does not guarantee ethically acceptable behavior. So this, I think you can go and look at that paper. It's a very interesting paper. And I think although it kind of holds the viewpoints, and although well, I wouldn't say that about this paper, but anyway. But essentially, what I'm saying is the discourse around the politics of AI is heavily driven by the Western world, which may not really appeal very well to kind of Eastern sensibilities and so on and so forth, and the global South sensibilities. So that's another arena of thinking that one might need to do, and this is an area of a lot of work these days as well. So let's look at a very basic example of how bias could creep into AI-driven decision making. And this is not even AI. What I'm going to explain to you is a very simple decision making process. It doesn't involve any AI at all. So let us say that there is a class of 7 students, and this is a marks: 68, 65, 55, 56, 70, 67, and 69. And you take the average, and the average marks is 64.28. Okay. Now let us say that what you're trying to do is you have been entrusted with this responsibility of identifying in a data-driven way which one is better of two teaching strategies that are given to you. And the first teaching strategy is S1, and the second one is S2. Let us assume that in this kind of a hypothetical world, we're able to create two copies of this class, subject one to S1 and subject the other one to S2, and see how it works. So you put S1, and you subject one copy of the class to S1, and you get this new distribution of marks. And that new distribution of marks has an average of 64.71. It is a significant improvement upon the class average in the previous case, right? Now you have 0.43 percentage point improvement. I think that S1 is a good strategy. Fine. Let's look at S2 now. S2 gives you a slightly more modest improvement, 64.42. So it doesn't make any sense to identify. Well, it doesn't. It's a no-brainer as to identify which one is better. You might say that S1 is better, right? And if you say that S1 is better, and you go ahead with it, you will essentially implement it, and then you might look at other teaching strategies that further implement it, that further improve your class performance further, and so on and so forth. But now let us look at another information about this class, which is basically the gender makeup of this class. And this class happens to have 7 students, out of which 5 are male and 2 are female. Okay, and this is like the distribution that we have in the STEM subjects, right? And STEM subjects are rather unfortunately heavily dominated by males. So when you look at these gender classes, and let us say that you compute the average, now you have the male average sitting at 67.8 and the female average at 55.5. There is a significant gap in achievement potential between males and females, which is about 12.3 percentage points. Now let us look at how S1 and S2 works. You can see that S1, in the case of S1, the male average has gone up by around 0.8 percentage points, whereas the female average has gone up slightly, has gone down. So you have actually widened the gap. Right now it is 13.6 percentage point gap. Whereas let us say that we look at S2, and here S2 actually is able to narrow down the gap. It is able to bring down the gap to less than 10 percentage points. And if you consider, if you happen to consider, which I think we should all do, that that the gender performance gap should be narrowed down, then you might consider S2 as the better teaching strategy. And why does this gender performance gap come in the first place? There is a lot of research into pedagogical literature, etc. So what they say is that many times, if you do, for example, if you do this kind of a data-driven teaching strategy estimation, you will go into S1. You're further making it unfavorable to females, right? So what this kind of a logic about maximizing the common good, and in male-dominated classes, in male-dominated teaching populations, etc., might have actually pervaded the community in such a way that the teaching strategies are much more favorable to males as compared to females. They appeal to male sensibilities as compared to female sensibilities, and that could be the problem. So here, what we now have is we've chosen S2 because it is good in narrowing down the gap. Right? It also gives a modest improvement in average in total performance. So why did we make this kind of a different decision now? We looked at S1 as the default decision earlier. Now we are saying S2 is a better one. What is the difference? The difference was that there was a representation flaw in the earlier case where a crucial determinant of performance, which in this case was the gender category, was not considered. And you should see that it is a crucial determinant of performance because there is a significant performance gap. There is a form of structural difference in the kind of marks that are secured by males as compared to females. Right? So that is a crucial determinant. Whereas if you might not consider, for example, left-handedness and right-handedness, because there is no structural discrimination there. Whereas pedagogical literature has told us that there is structural differences along the gender axis. There might be structural differences across a class axis as well, across maybe caste axis and all these kinds of things as well. And there is a significant modeling flaw. And this is something that I would like to emphasize here. Let us say that we have a distribution of marks, and if the distribution is unimodal, in the sense that it is like a bell-shaped curve with points being clustered around the average, then what you might say is that it is very well represented by the average. Whereas if you have a bimodal distribution, which means that there are two peaks. Here you have a peak at around the high 60s and the peak at around the mid 50s. If we look at two peaks, and the two peaks kind of distribution is never well represented by the average. Just think of it this way: there is a peak at 30, there is a peak at 50. The average is 40. 40 is neither representative of the first peak, neither representative nor representative of the second peak. And nobody in the data set has an average of 40, but still we get the average as 40. So average is a good representation only when you have a unimodal distribution. Otherwise, you might be the populating maybe median, etc. And there's an evaluation flaw as well. Because you have a male-dominated class, if you just simply take the raw average, just taking the average would itself be biased towards the males. For example, because there are 2.5 times as many males as there are females, The problem here is males have 2.5 times as much influence on the average as compared to females. And this is something that we often don't take into consideration. And here, what I've illustrated is that if you choose S2 instead of S1, due to the higher fairness of S2, we settle with a lower improvement in aggregate performance, which also brings in this frontier of tension between fairness and average. The average is a utilitarian metric in the sense that it computes equally across the entire population. So these two are often in tension. And what I just wanted to also see here is that many times when you look at if computing simply computing an average could lead to these kinds of biases, think of computing a neural network over the population, neural network over the data. I mean, there could be so many ways of bringing in bias into that kind of a decision-making scenario. This computing average, which is very visible, which is very transparent to the human eye, itself has such a big problem. So when we talk about other kinds of things, and you can imagine the kind of issues that would contain about it, right? So the takeaway here is that representations could hide pertinent information. If we do not choose to represent gender, we will never realize the problem. And what is the kind of golden rule in order to identify which one should be taken or which one should not be taken in terms of representation? So one way to think about it is whenever there is a structural discrimination along any axis, or whenever you suspect that, might as well take that into the information, take that into the representation. For example, if you suspect that there could be a structural discrimination along things like maybe caste or maybe nationality, etc., just take that into consideration, not only check for that. And if you don't have any evidence of it, just ignore it, because as we said earlier, we won't look at right-handedness and left-handedness as a frontier of discrimination, because there's nothing apparent there. And modeling could be biased as well. So assuming unimodal distribution would be biased towards the majority group. And utilitarian metrics are not everything. Aggregate utility and fairness are often in tension. And this is something that will keep coming up in the next few slides as well. So when you talk about aggregate utility, some of the utilities over everybody, then that is often in tension with notions of fairness. And this is a quote from Cathy O'Neill, who wrote a popular book called Weapons of Math Destruction. So she says, I would argue that one of the major problems with the blind trust in algorithms is that they can propagate discriminatory patterns without acknowledging any kind of intent. So earlier, when we decided, without looking into gender information, that S1 is a better thing, we did not have any intent of being unfavorable to being discriminatory towards females. Right? We never had that intent. We just did an innocent way of, or a kind of very simple way of, very naive, innocent, and simple way of identifying which one is better, and we identified that S1 is better. But it so happened that it was about propagating, actually deepening discriminatory patterns in that particular case. But utilitarian methods have come to be considered natural to optimize for machine learning. And that is partly because machine learning, the way it has grown in the last maybe 4 decades has been extraordinary. And these last 4 decades are also what we sometimes call as the neoliberal decades, where profit-oriented decision making has kind of overshadowed every possible other metric. So in the sense, when you're talking about when you're looking at and this is not just within algorithms or anything. This is just within the entire political circles and the way society functions. Profiteering has had an overarching effect over other kinds of things, and it has overshadowed a lot of the other kinds of metrics. And utilitarianism doesn't just come from Western cultures and Western societies. For example, Gandhi had a significant criticism against utilitarianism. He says that a votary of Ahimsa cannot subscribe to the utilitarian formula of the greatest good to the greatest number. He will strive for the greatest good of all and die in an attempt to realize the idea. So the point here is that if you strive for the greatest good for the greatest number, you essentially may not be able to consider that each individual in isolation, or each individual's circumstance. Gandhi, of course, as you all know, pioneered some of the movements between the socially backward groups, such as the Harijans and so on. So when you talk about the greatest good for the greatest number, this small category of people, or might not be a small category, but essentially let's assume that it's a small category of people. And you will never be able to do justice to that category because they are a minority. Right? And even when we talk about, let's say, infant mortality and data decision-making in IT, to do that, we will never realize that there is this small population within an Adivasi community which has a significant infant mortality. So, so this is about putting yourself in the feet of putting yourself in the shoes of the kind of population which is heavily disadvantaged within the current societal setup. So, if we are not conscious about identifying and reducing bias, we will produce bias. Let's look at what fairness is. So, what is fairness from the context of machine learning? There have been two notions of fairness. We look at the first one here. The first one is about procedural fairness. You would say that this, when you look at this kind of a picture, you would say that it is unfair. And why is it unfair? It is unfair because it violates the appropriate procedure of crime. There is a road which has two lanes. One lane is for onward traffic and the other lane is for return traffic. And you see this KSRTC bus which is coming on the other lane. And I'm not putting it. I'm not even interested in putting that stereotype in KSRTC at all because I think that they're wonderful drivers there. But essentially, there's a big bus which is coming on the other lane, right? And it is coming on in such a way that it blocks the traffic. It puts these two-wheelers who are traveling on their lane at a significant equivalent continuance. So it violates what is called as procedural fairness. So what is procedural fairness? Procedural fairness is about the institution of a well laid out and appropriate process. If you say that there are 5 lanes on the road and 4 lanes are one way of traffic and the other lane is for the other traffic, if you are unable to justify why it is the case, then you could think of it as a biased process, right? So you need to talk about instituting a well laid out and appropriate process, and then you should also be able to monitor and enforce conformance to that process. So, and machine learning can be thought of as similarity-oriented decision making, and its fundamental tenet is that similar objects be assigned similar outcomes, and this is sometimes also called individual fairness. So when can you have a violation of procedural fairness in machine learning? One possibility is when the process that you have laid out is inherently problematic, right? And there has been criticisms from various kinds of enlightened people within the 20th century social reform movements, where they say that, for example, I think it was Martin Luther King who said that there is a moral responsibility to disobey unjust laws. And I think Gandhi used to say that an unjust law is a species of violence, and getting arrested for that and getting arrested for protesting against that is even more so, and so on and so forth. So essentially, when you process or when you're talking about mixing up things here, but essentially it is to say that this notion of procedural fairness pervades societal reform movements as well, not just AI, but pervades societal reform and social reform movements. So institution of a well laid out and appropriate process and conformance do not ensure conformance to that process, it doesn't make sense. Similarly, if a process is inherently discriminatory and exclusionary, for example, I think the social reform movements in the 20th century in Kerala, like the Merchant Satyagraha and so on and so forth, we're about that. We're about saying that this particular process of denying entry of people from a particular caste into the premises of a temple are considered discriminatory. So that's you might see these kinds of pictures whenever some of these entrance examination results are out, right? So you have these coaching institutes saying that our folks got 10 ranks within the top 100 and so on and so forth. All these kinds of things. So if you have this kind of a picture, when you come across this kind of a picture, what kind of often strikes you is that it is heavily male, right? It is mostly males. Whenever you're talking about JW, so this is a picture about the JW entrance and its results as advertised by a coaching center. So most JW toppers are boys. But JW is procedurally fair, and this can be said of KE, and this can be said of anything for that matter, right? It is procedurally fair. It doesn't ask you your gender or your gender position. It doesn't discriminate you on the basis of that information. But so it so happens that it ends up producing tools where most of the rewards are distributed to males as compared to females. And most MLEs and MPs are male, but elections are procedurally. Well, of course, in Kerala, we have the local body elections where there's a particular reservation mechanism, etc. But essentially, if you don't have that mechanism, you end up having most MLAs and MPs of land in the legislature and the parliament and so on. So this brings us to what is called as distributive fairness. This says that procedurally fair methods could still distribute rewards unfairly. So if you have a fantastic method in order to identify suspicious images, and it is very fine, but still it might end up identifying developed areas as more suspicious than maybe high class areas and so on and so forth. Right? So distributive fairness is about representation balance, it's about equality of outcome, and people who are similar on task relevant attributes. And this is where we played this to machine learning. People who are similar on task relevant attributes may need to be treated differently to ensure equality of outcome. So let us say that there are two students who got 45 marks in an exam, right? And one of them is from an OBC background, the other one is from a general category. And the general category cutoff is 50 and the OBC category cutoff is 40. So the second one, the OBC category student might be regarded as qualified, and the general category student might be regarded as unqualified. And why are we doing this way? We're doing it this way because we want to ensure enough reservation category students within the qualified category, within the qualified class, right? So you have different thresholds for marks for different people, for different groups in this reservation system. And that, in a way, we can think of it as violating the similar individuals with given similar outcomes in kind of tenet. And we need to violate the tenet in order to ensure that there is distributed fairness. And there are the leading the Western world. We talk about policies targeted to level of the gender pay gap. So whenever we're talking about recruitment, etc., we say that in STEM there are a lot more males than females. So we need to find more female qualified students. So among the qualified students, we might actually prefer to recruit females or prefer to recruit people from certain categories as compared to others. And policies targeted to enforce the diversity in workforce as well. And as I said earlier, social reform has its implications, has its underpinnings on distributed fairness as well. For example, Ambedkar pioneered the fair representation of SCs and STs through a constitutional provision in India's constitution. Whereas you might not recognize the next person there. His name is Mandal, and you might remember the names of the commission that was headed by then called the Mandal Commission, that was about fair representation for policies and so on. So the two notions are significantly different. In the sense, procedural fairness is about eliminating disparate treatment. It's about treating everybody similar. It's about equality of opportunity. It's about ensuring fair process, even the level playing field, and that similar individuals get similar outcomes. And we look at what is called as access or regulatory fairness within that context. Whereas, and this is called individual fairness within machine learning literature. When we talk about distributive fairness, we're talking about eliminating disparate impact. We are saying that the benefits of AI, the benefits of technology, the benefits of any social policy should be fairly distributed across the population. So the benefits of having an IIT and 1,000 seats across IITs should be felt across different sections of the population, right? Or any university for that matter, any kind of reward. A representation balance, distributed justice, and dissimilar people may need to be treated similarly to ensure outcome balance. And we can also say that similar people may need to be treated differently to ensure outcome balance. And this is called as group fairness. And these two are sometimes argued to be in tension, because individual fairness and group fairness do not necessarily go well with one another. As I said earlier, dissimilar people may be treated similarly, so which means that similar individuals get similar outcomes, but potentially they violated in some particular context. So we will look at a particular machine learning method around fair decision making, and we will come to the notion of come to the case of clustering. But before we go into the algorithms, may I pause here and see whether there are any questions that I might want that would be useful to address at this point. I don't know whether there's a chat option, but if somebody has any questions and try to speak out, you can also type it in the chat. Or please unmute and speak. Is there any?
Participants, yeah, can post your queries in the chat box. Participants, if you have any queries.
So just wait for 10 more seconds to see if there are any more questions. Otherwise, we'll just move on to some of the algorithmic aspects of. Okay, so we can have the questions at the end as well. So keep the questions and type in your questions into the chat box and we'll take it all of them. So we look at this task called clustering. And clustering is a specific task within unsupervised machine learning. And here we will look at what is called as partitional centroid clustering. So let us say that there is a task relevant representation space. Okay. So the task relevant representation space says that there is a meaningful similarity positioning within the space. If two objects, if two dots are close to one another, each dot represents an individual piece of data point. If two dots are close to one another, it says that they are very similar to one another. Okay, and if they are very far away, they are considered to be dissimilar. And when you look at clusters, and when you look at clustering is about putting these dots in groups in such a way that the data objects within a group, within each group, are very similar to one another as compared to data objects across groups. So if you have a cluster of objects which are very close to one another, they would be put in one cluster. And these clusters, as I've shown here, are red, blue, and green. Red, blue, and green. Yeah, and that is because the color doesn't really matter because it doesn't really say anything about it. It's just a way of identifying the clusters, identifying the separate clusters. Okay, so each cluster also has a prototype, which is shown by this X mark, which is kind of a typical object within that cluster. Let us see how we can do clustering. So if we do clustering this way, and this is the way that we do clustering. If we use simple algorithms such as k-means. K-means is an algorithm which existed since 1960s. 1967 was when it was first published, and it has been very popular still. So if we look at that top right object, and let us look at this as the output of k-means clustering. If you look at the red cluster and look at the top right object in that red cluster, okay, top right object in that red cluster, and find its closest neighbor, and its closest neighbor is an object in the blue cluster, okay? And we have joined that by using a line segment. And let us now look at its neighbors within its own cluster, within its red cluster, and you have these four neighbors within the red cluster. And if you measure the distances, and if you look at the distance distributions, you will see that the black distance is the smallest, and the red distances are slightly higher, and it goes higher going forward, right? And what you can see here is that when you look at it in the backdrop of this principle of machine learning, that says that similar objects should be treated similarly. This object, this red object, and its closest neighbor, which is the blue object, are different outcomes. Treated similarly within the notion of clustering says that put in the same cluster in some way. That is one interpretation. So this clustering violates individual fairness for that red object because it puts the red point and its closest neighbor in different clusters by assigning them different outcomes. So some amount of individual fairness, individual unfairness may be inevitable while allocating decisions based on a global criterion of optimizing for common good. You cannot enforce that every pair of objects which are closest and which are near neighbors should be put in the same cluster. Because if that is the case, you might not be able to find a coherent cluster, or you might not be able to even find a cluster. So this is something that we come across in societies in decision making in general, right? When you optimize for a common good, when you optimize for the cumulative good, you might tend to make some subpar decisions, suboptimal decisions for certain individual objects. Let us say that you're trying to locate ration shops in an equitable fashion. You might still have a person who needs to travel 3 kilometers to the nearest ration shop because they are located in an area between the boundaries of two ration shop catchment areas, etc. Okay. So the point here is that some amount of individual fairness violation might be inevitable, but we need to make sure that this individual unfairness is a reasonable outcome of optimizing for the common good. We cannot say that we will violate all individual fairness, but you need to make a condition, make a case that this individual fairness violation is inevitable in order to optimize for the overall common good, which is a higher overall comprehensive justice. So here I have this is a paper from my group. Savita was a PhD student, and she's now doing a postdoc in a European university. So here I have an illustration of two clusters. So let us say that there are 5 data objects, 4 objects which are put in the blue cluster, and 1 object which is in the red cluster. So the red cluster as centroid of the prototype is itself, because that if there is only 1 object in that cluster, right? And the blue cluster has a prototype which is located at the centroid of these 4 objects, which is basically this this black background circle, right? Sorry, black bordered circle. So now what we look at in this paper is something called representativity fairness, which is to measure the distance between each object and its cluster centroid. Okay, its cluster centroid. So you take a blue object, you measure it to its cluster centroid, which is a blue cluster centroid. And you take a red object and you measure it to its cluster centroid, which is a red cluster centroid. So as you can see, the red cluster is at its own point and its own centroid, so the distance is 0. So I have the left the table there where I show the left column as a vector. So you have R of 5.5, 5,5 is the top right corner of the square where you have the red object. The red object is at its own cluster centroid, so it has a distance of 0.00. Whereas the blue object, somewhat in the middle, which is 3.3, 3,3, 3,3 is in printing of this as a Euclidean space, is at a fair distance from its cluster centroid, which is at a distance of 1.77. And the other objects have a distance of 1.06 and 0.79, etc. So now you can see that this vector is a notion of representativity, which is to say that each object is as well represented by its centroid as shown by the similarity. And in this case, we have the distance. So distance is an inverse notion of similarity. So this says that the red object is very well represented by its cluster centroid, whereas the 3,3 object is very limited in its representation by the cluster centroid because it is very quadratic. And we have made this assumption that this Euclidean space is a meaningful space in the sense that 2 objects being close by and means similar. So when you look at the average distance here, you have 0.88. This is the average distance of an object to its cluster centroid. Now let us say that we choose the cluster representation, we choose the cluster differently. We say that the 2 objects at the top right corner of this space are put into the red cluster. So you change the clustering in such a way that this blue object is switched over to the red cluster. Now you have a different representativity vector. The blue cluster centroid moves further inward to the blue cluster because it is a centroid, right? And centroid basically means it's the average of those blue objects, and that is where it is. So now what you can see is R5,5 is now no longer 0. Its cluster prototype is no longer itself, but it is further away. It is at a distance of 1.41, and similar is the distance for the cluster prototype from 3,3 as well. So now, as you can see, this red vector, there's a right vector there, right? And it has a different distribution. The difference the distance of each object from its centroid has changed. Now, what is the quantitative nature of the change? You can see in the left vector, you have the smallest number of 0.00 and the largest number of 1.77. So there was a wide distribution, right? The distances the differences were significant and wide. Whereas in this case, the smallest is 0.74 or 0.47 and the largest is 1.41. The distribution has become narrow. The distribution has become more uniform in that now the average has gone up, right? The average distance of each object to its centroid has gone up by around 10 percentage points. 0.88 has become 0.96. However, the distribution has become fairer or more uniform. So this is kind of trying to enforce, this is a way of trying to enforce representativity fairness by making sure that this representativity vector, as we call it, should be made more uniform And if you were to make it more uniform, it comes at the cost of computing average. The average might actually go up, might actually become less representative on an average. But essentially, all the objects are fairly representative, since they are likely represented better as compared to the other ones, as compared to their neighbors, as compared to the objects in the objects across the data set. So this is kind of a tension between representativity and average, right? Representativity fairness and representativity average. So as you can see here, by making objects on an average more distant from the cluster center, you can get more fair or more uniform vectors for the representativity. So representativity fairness can be enhanced by changing cluster assignments. Let's look at group or distributed fairness within cluster. So let us say that we have, let's take a particular scenario. Let's say that we have a job application, a job description that has been put in. Let's say that there are 90,000 railways jobs that have been put out. And you have 2.8 crore people applying for these 90,000 railway jobs. And this was a real scenario in 2018 in India. Because in India, as you know, like government jobs are highly coveted because of their stability and so on and so forth. And now, how can you deal with this kind of an application setting? You cannot hire enough people to be able to do this 2.0 crore going through each of these 2.0 crore applications, because that will be itself another hiring task. So what you might do, I'm not saying that the Indian Railways did this, but what I might do is to say that is to make use of clustering in order to do this, in order to optimize for this decision making. Which is to say that you build clusters of similar applications. And when you build these clusters of similar applications, what happens is each cluster will have very similar applications within that cluster. So you can look at some of these applications, some applications within a cluster, and make judgments that could be applicable across the entire cluster. So you might look at some of these applications and see that, well, this seems to be a cluster with reasonably highly qualified people. So let us go ahead and shortlist this. And you might look at another cluster and say that this seems to be a cluster with which are not so qualified, so we might actually discount it. In another cluster, you might find a mixture of people of different backgrounds, and where you might actually say, well, it doesn't seem clear to me as to what needs to be done, but let's do another clustering event and cluster it further into 10 clusters, and we'll look at it then. Okay. So this is a clustering oriented decision making model, which could be used for job application shortlisting, or could be used for other kinds of things as well. For example, you could look at CCTV images and cluster them and identify suspicious and label clusters as suspicious or non-suspicious, etc. The problem here is, like, let us say that you're applying it in the job hiring scenario. Your clustering algorithm might generate clusters that look like the left-hand side clusters. It might generate some clusters which are heavily male dominated, and some other clusters which are heavily female dominated. That by itself is not a problem. But if you tend to have a societal stereotype that males are more qualified for this job, then this form of a clustering opens up a pathway towards gendered decision making. Okay? Opens up a pathway towards gendered decision making in the sense that somebody looking at a cluster and seeing mostly male applications might think that, okay, I know that males are qualified for this job, so might as well shortlist this. So it might end up getting a shortlist which is significantly male oriented as compared to females. Whereas another way of saying it is another line of attack for using clustering is to say that I will enforce that the clustering algorithm is built in such a way that each cluster will have 50% males and 50% females. And if that is the case, whatever way you do this cluster level decision making, you will always end up with 50% males in the shortlist and 50% females in the shortlist. Okay? So this is a way of ensuring that if you have this is a way of fair clustering. Essentially, which says that you should ensure fairness within every cluster, ensure fairness or diversity within every cluster. So your eventual shortlist or eventual list would also be uniform and fair. Right? Would also be diverse and fair. So what we did was to look at this kind of a representation disparity within clustering. Okay, so let's look at this kind of a data set. Here we have here are some data points labeled by blue, and some other data points labeled as red, right? And let us say that blue is basically males and red is females, and red denotes females. And if you do a simple cluster, what you might get is these kinds of clusters, nice oval-shaped clusters, very coherent clusters, and so on and so forth. But the problem here is the top cluster has a significant red population, predominantly female, and the second cluster has a predominant male population, right? So what you might do is to kind of assess how fair these clusters are. And if you want to assess it, you can look at Euclidean distances between these vectors. 0.5, 0.5 is a vector, 0.67, 0.22 is a vector, and you can measure the distances between these two vectors. And you can do the same for the other cluster, and you can sum them up, and you can identify that the cumulative fairness disparity is this 0.1156. So what do you do? You might want to enhance this representation parity. So it should actually be enhancing representation parity and enhancing representation disparity. Enhancing disparity doesn't make sense, so we're making things even worse. So what you might do is to generate clusters that look like this. These clusters are not so bell-shaped, not so bell-formed, not so oval-shaped, not so compact, not so concise, and not something that you would actually be willing to kind of justify. But it is justified in a different way, in the sense that you look at this representation within the clusters, you will find that there is a 50% representation of males and females within each cluster. So if you measure this fairness disparity, you end up getting 0. That's a cumulative fairness disparity, right? And so this makes it a much more attractive cluster. This is like in our pedagogic teaching strategy example. This enhances fairness, but at the cost of the shape of these clusters. So you end up creating slightly less coherent clusters. So how do you manage to create these clusters in the first place? And that is what we did in this paper. This is considered across 2 PhD students, Aditya and Soumya. So we want to simultaneously optimize for clustering coherence and fairness. We want to make coherent clusters, but we also want to make them fair. And these two are in contradiction, right? So how do we manage this? What we did was to take clustering diversity as one objective function. In machine learning, when we work with objective functions, the way we work is we define an objective function and look at the structure of the objective function, identify an optimization strategy, and we optimize for that objective function, right? Using the optimization strategy. So here we said that instead of optimizing just for cluster diversity, which favors creating very coherent clusters, we will instead optimize for cluster diversity plus fairness disparity, which is controlled, the relative importance of which two are controlled by a relative weighting term, which is lambda. Right? So what we did was we took fairness disparity as an optimization term and cluster diversity as an optimization term, put them together by using a weighted sum combination, using a relative weighting of lambda, and then optimize for this entire thing. And in the process, we get clusters that look like that are closer to this. Actually, it might be somewhere in between this and this. So there might be a little bit of unfairness, but it might be more coherent. This one is about ensuring fairness at the cost of any amount of coherence and problem there. Okay, so we will next go into outlier detection, which is a significantly different task. But may I ask how much time I have left? Just to understand.
So can we wind up within 10 minutes, sir? 4:30?
Yeah. Okay.
Yeah.
Okay. 10 minutes. Right? Okay. Yeah. 4:30. Yeah. Okay. No problem. So let's look at outlier detection. So here I will just outline the spirit of fairness within outlier detection. Okay. I won't go into the details of the algorithms until at the time. So what are outliers? Outliers are observations that deviate so much from other observations as to arouse suspicion that it is generated by a different mechanism. So here in this case, we can clearly see that this red fish is an outlier because it goes in a different direction. So outlier detection is heavily used within societal decision making. For example, if your health pattern is an outlier, you get maybe a very high insurance premium. And if your kind of situation is an outlier situation within in certain cases in the Western world, they also give you a higher premium if you're living in a notorious locality, because they think that notorious localities will have higher risk. and your car is likely to be stolen more than people who are living the lower risk and so on. But in India, of course, we know that it is all the same premium for any car wherever the person is located. And if your kind of travel behavior is considered as an outlier, you stand at risk of maybe denied a visa. And sometimes outlier detection is used in predictive policing as well, where you find some non-mainstream behaviors and you go to those non-mainstream and we go and look at these non-mainstream behaviors and consider some of them as outliers, and we go and talk to those people and see what is the context of their behavior. This has a significant issue with respect to jurisprudence principles as we outlined earlier. But I'm just talking about how it is used in the normal sense. I'm not saying that it is legitimate to be using these kinds of things. Okay. So, as we said earlier, when you talk about machine learning models, it is implicitly biased. In this case of outlier detection, identifying normality, that's what outlier detection entails. It entails, it actually implies that you need to build a model of what is normal. And the model of normal is likely to be more influenced by the demographic category since it is more prevalent. This could lead to picking out demographic groups more frequently as outliers. Actually, some outlier detection papers almost say that we train it on normal data, we train it on the entire data, and then measure each person's deviation from that model as a notion of outliers. And that is a very popular outlier detection paradigm, and that is inherently biased against minorities. So if you have a population ethnicities that look like this, let us say that most of the population is in that orangish brown kind of area, your outliers may look like this, where the minorities might have a significantly higher presence among the outliers as compared to the general population. Whereas fair outlier detection is about ensuring that the outlier ethnicities mirror the population ethnicity distribution. So essentially, the inconvenience of being classified as an outlier is distributed fairly across various demographic groups. So this is a paper that we did, but I think I won't have time to do. But let me just try and go through this a little bit. So this is something called local neighborhood-based outlier detection. So local neighborhood-based outlier detection uses a paradigm where you consider an object, take an object, and look at its neighborhood. We draw an R-shaped circle around it, R radius circle around it. R is just the radius of the circle, and you look at the objects within it, and you compare this black object in the middle with the neighborhood objects, which are these 5 objects that are located within that circle. And if you do the comparison, and if you identify that this black object is significantly different from its neighborhood, you classify it as an outlier. So in the neighborhood-based outlier detection, the problem here is that minority objects get compared with their neighborhood, and this neighborhood is sampled from the entire data set, and that neighborhood might actually end up being majority oriented. So thus minority objects are more likely to get compared with majority objects just due to the relative abundance. Just due to the relative abundance of these majority objects. And you normalize the scoring by making use of a sensitive attribute membership. That is what we did in this paper on fair outlier detection, which is published in PAIS 2020, and there is an extended version that is recently published in the journal as well. So the problem here is that minority objects get compared with the majority, with the majority oriented population, and that basically causes a degree of unfairness. So the points here is that data-driven AI is often unfair. And this is of much concern when making decisions that impact individuals and societies. Patterns in data could be unfair. And let us say a small thing here. For example, let us say that you're doing retail decisions. You're running a toy store and you're making retail decisions. And you might be building an ML model. And the ML model might actually capture the fact that male kids or parents with male kids tend to prefer blue toys and parents with female kids tend to prefer pink toys. Well, it's my opinion that we should never be discriminating the color of the toys and related to kids, but essentially, if we capture this kind of a correlation, it might actually suggest that we build a blue toy aisle and a pink toy aisle very, very far away from one another because they don't overlap. Because customers who buy blue toys do not buy pink toys, etc. So that's a problem, right? Because it's propagating a stereotype. And design of algorithms could be unfair. And there are various varieties of unfairness. If you would like algorithms to be fair, we need to design for fairness. These are 2 kinds of unfairness, and these 2 are in conflict. In fact, there's a tutorial called 21 definitions of fairness, where the presenter talks about 21 different definitions of fairness, and there are significant conflicts across time. So fairness is often in tension with accuracy or efficiency, and fairness comes at a cost. If you need to be fair, you might end up taking a hit in your utilitarian metric, and the utilitarian metrics are often correlated with profit and and money, etc. We're talking about the amount of labor saved, we're talking about the speed in which things can be run. We're talking about generally accuracy, which is essentially what we're metric. So if you can achieve high degrees of fairness at low cost of accuracy, we can claim success, and that is the way fair AI literature has been looking at it. And AI ethics comprises two kinds of, the way I see it is there are two streams of things. One is interactive stream, where you're talking about ethics while dealing with robots, etc. So there you're worried about trustworthiness, you're worried about interpretability, you're worried about privacy, etc. Whereas there is a normative stream, which is about fairness. And this normative stream is very different from the interactive stream, in the sense normative stream takes principles from political philosophy, whereas the interactive stream takes principles from cognitive science. So you're often asking about what is the right thing to do, when you talk about this normative stream, right? What is the right thing to do? Right? You're not even finding patterns, you're not even people want to decide. But a random decision-making model could tend to be very fair, in the sense that you're not discriminating across any categories. So you might end up giving equally or proportionally to different categories of them. Example from a coastal fishing village called Chellanam, in Second Year Mother watched the movie that's located within that. There, it's a fishing community, and they have limited capacity to go out to fish. Where let us say that there are 100 people, and the capacity is only there for 50 people to go out. They get everybody assembled in the morning, and they randomly pick 50 people to go out to fish. And there's a random allocation. But essentially, this has been covered by various news articles. It's a random allocation. 50 people go out to fish, and the other 50 people do something in the shows. And when the catch comes in, they auction it, and the proceeds are distributed according to two remuneration patterns. One is a higher remuneration given to people who went out for fish, slightly lower remuneration. As what would you do? You would say that people who come first would be served first, because you want to wake up early, you're not sure that they will wake up early, and all sorts of things, right? It creates all sorts of issues for you. You might trigger a race to the bottom in that sense. So everybody's life is disrupted because of this because of trying to optimize for this first come first served kind of approach. Whereas if you have this randomness oriented approach, everybody can come to the shore, to the beach at maybe 6 a.m. or whatever it is, right? And they are making random allocation here. And the thing about this is, if you get a random allocation, you're equally likely, in this case where the capacity is 50%, you're equally likely to go out a fish as compared to starting outside. So across 30 days, you might get 15 fishing days and 15 non-fishing days. In which case, your average income would be 400 for the fishing, 400 for the non-fishing days, and 600 for the fishing days. Your average income is 500 rupees per day, right? Whereas if you so this is a kind of across a temporal kind of session, across a long range temporal period, everybody gets 50% for 500 rupees per day as a wages, because it's random, because this randomness gets factored in at that level. So, so essentially, this is what we do, and this I just wanted to illustrate this as we often think of random decision making as a stupidity oriented decision making, whereas randomness, controlled randomness, can be used in a way that kind of ensures that there is a notion of fairness in innovation, fairness in distributing rewards, fairness in distributing positions, etc. So I think we'll stop here, but I think I overshot by 5 minutes. It's 11:05 here, which means it will be 4:45 there. So yeah, I'm open for any questions or comments, and I'll just unshare my screen. Yeah.
Thank you very much for your Actually, sir, it is a very thought-provoking session, and altogether different approach. So in the morning inaugural session, our Pro Vice Chancellor was talking about AI's other part of AI, which was most of the algorithms and applications, they are tracking the behavioral aspects of the human. So actually, this is another view of things.
Yeah, in fact, there has been a significant issue with, I mean, AI and machine learning works on this fundamental assumption that there's a historian called Yuval Harari who has written a book called Sapiens, and where he says that the fundamental, I think it's which is his next book, says that the fundamental assumption in this society is data is